So we're trying to discuss, we're discussing supersymmetry, which is some sort of symmetry, some sort of symmetry implemented on Hilbert spaces of quantum theories. Okay? To start this discussion, let me remind you how ordinary continuous symmetries with a continuous parameter are implemented in quantum mechanics. Okay? So as you know, ordinary continuous symmetries are characterized by their generators. Okay? And let's say that the generators are labeled GI. Okay? And as you know, when we study, maybe this board is better. Okay. When we study ordinary symmetries, we specify the commutator between two generators, GI, GJ. Okay? And we specify this as some Fij k, some linear combination of the other generators. The fact that these commutators are a linear combination of the other generators tell you that the whole system closes on itself. Okay? Now, these generators here obey a sort of identity that people sometimes call the Jacobi identity. Okay? And this Jacobi identity is the following statement: Gi commutator Gj Gk cyclic sum is equal to 0. What do I mean by cyclic sum? I mean there are three terms here. The first term is ijk, the next term is kij, and the next term is jki. Okay? Now, for a mathematician, this is a non-trivial identity. But in the situation where these generators, situations of usual physical interest, where these generators are some operators acting on a Hilbert space, this identity is not a non-trivial identity, it's a triviality. It's just a statement of 1 is equal to 1, 2 is equal to 2. And to see that, let's just open this out. Okay? So we've got the cyclic sum, and then we've got Gi and Gj Gk minus Gi Gk Gj. Okay? And then minus Gj Gk Gi plus Gk Gj Gi. Okay? And now you notice that these two guys are equal up to a cyclic transform. So in the cyclic sum they cancel. Similarly, these two guys are equal up to a cyclic transform. So they cancel. It's non-trivial if you don't assert that these operator products are associative. You see, a mathematician, when she defines a Lie algebra, will define the bracket, but will not define a product between two G elements. However, when these guys are implemented on a Hilbert space, it's not just the commutator that's defined, but the product itself. It's like the operators can multiply. And as long as that multiplication is associative, that's all we've used here. Okay? This thing cancels. So it's just a triviality in the context of physical interest to us. Okay? And this Jacobi identity, is an integral part of the study of Lie algebras. From the abstract point of view, it's very useful, even from the non-abstract point of view, though it's a trivial identity. Okay, now, one way of motivating the study of supersymmetry is the following algebraic observation, which I'm going to make. And then we will leave this mathematical way of thinking and turn to more physical ways of thinking. And the algebraic observation is the following. Suppose you had suppose you had two classes of operators on a Hilbert space. Okay? One class that you called Bosonic, and the other class that you call Fermionic. So far, these are just names. Okay? So there's Bosonic operators and Fermionic operators. Okay. And then you define, so let's call the bosonic operators Bi and the fermionic operators Fj. And sometimes I will use the symbol Am to denote an operator that could be either bosonic or fermionic. Okay? And then you define the analog of this commutator as follows. You define some sort of bracket, I don't know, maybe we'll call it this kind of bracket. Some symbol, such that this is the commutator when both A's are bosonic. One A is bosonic, the other one's fermionic. But it's the anti-commutator if both A's are fermionic. So that's my definition of this bracket. Okay? Then, suppose you've got a system in which you've got these A operators such that under this bracket, it happens that this bracket, its linear combinations, generates just linear combinations of these other A's, just like we had in the case of Lie algebras. Okay, so we've got linear combinations of these A's. Okay? Now, with this bracket, the following thing is true. The following thing is true, that just in the sense that there was this trivial Jacobi identity for Lie algebra brackets, there is a correspondingly sort of trivial in the sense that trivial if it's implemented by operators on Hilbert space, trivial if the product is associative. Okay, a Jacobi identity for the brackets of three of these objects. And the identity goes basically as follows. What you do is to make the I, Aj, Ak. This is a very cumbersome notation, I apologize. Just don't want to mix you up with some other notation that has some other meaning in your head. So I made this up. Okay? Now, we do this and we do the cyclical sum. However, every time in the cyclical sum, you take the cyclical sum involves reordering, right? Because this A goes in the next term. So let me write it out. So there's this, then there's plus AK, AI, AJ, plus the other guy. Okay? Now, this guy has taken an AK through the AI and AJ. Okay? So, if in your head associate a sign with taking things through. And the sign is that whenever two fermions go through each other, you pick up a minus sign. Okay? So, if AK was fermionic, if AK was bosonic, there's no sign. If AK was fermionic and one of these other two were fermionic, there will be a sign. So this will not be a plus, but will be a minus. Okay? Similarly for the next term. Is this clear? Okay? This is a new idea, a new quantity you can look at. Okay? And you can, by checking all the various cases, by trial and error, convince yourself that this vanishes as trivially as that vanished. So I'm going to check one term for you, just so that you see this. It's not plus. This sign is whatever. It's a sign which is determined by the statistics. Right? You start with a plus and then correct it for counting the number of times you take a fermion through another. Is this clear? So for instance, suppose all three were fermionic operators. The most far from the bosonic case. What would this Jacobi identity be? Well, it would be Fi. Now they're all fermionic. We don't have to use funny notation for this bracket. We know that the commutator of a fermion with a boson is a commutator. But the commutator of two fermions is an anti-commutator. That was the rule, right? This plus cyclically symmetric.
Why you are using
Because this compound object is bosonic. So So that's the rule. That, okay, I should have said also that the brackets satisfy this rule. Okay, that it's got the Z2 grading. So that if you have fermion with boson, you will get fermions. Boson with boson, you will get bosons. And fermion with fermion, you will also get bosons. That's the bracket has the Z2 gradation in that rule. I should have said that.
But you have taken all these fermions, right? So if like these two will give a boson, but you still have fermions.
That's right. But taking the bracket of a fermion with a boson is the commutator. The only case that you get an anti-commutator is two fermions with each other. Okay, that's why this is the commutator. So now let's open this guy out. Okay, so this is Fi, Fj, Fk plus Fi, Fk, Fj minus Fj, Fk, Fi minus Fk, Fj, Fi and cyclically sum. And now we've got Ijk here, but you've got Ijk here. So this cancels this. And this is Ikj, this is Ikj, so this cancels this. Okay, and you can check it for all the other cases. There's only one other really non-trivial case to check, which is two fermions. Yeah?
Fermion crosses boson, there is no minus.
No, no minus sign.
Just when fermion crosses.
Only fermion crossing fermion is a minus sign. That's the rule. So there's one other non-trivial. Every other case is basically, you see, if you have one fermion, then there are no signs, and all brackets are commutators. So it's the same algebra as we checked for G's. Okay? There's one other case to check, whether there are two fermions, and you can do it, but I'll leave it to you. Okay? So so when you have these, you've got two classes of generators. You call one class fermionic, the other class bosonic. The bracket obeys the Z2 rule. Right? Boson with boson gives boson, boson with fermion gives fermion, fermion with fermion gives boson. Okay? And if you've got such a bracket, then this bracket automatically satisfies this modified Jacobi identity. Now, a lot of the mathematical work that went into characterizing Lie algebra started with the Jacobi identity. And mathematicians were able, but after physicists, note, I think these objects were first discovered in physics. But mathematicians are then able to take this as the starting point and generate a large theory of this symmetry algebra. The algebra of operators on a Hilbert space that obey these kind of mixed commutator anti-commutation relations. And we get many of the same nice things that when we study group theory with this funny structure. Okay? So from a mathematical point of view, this is one strange mathematical reason to be interested in these objects. However, we are physicists. And if mathematicians are interested, that's good for mathematicians, but it's not enough for us. So the real reason we're interested is that these structures arise. Okay, so this is the general mathematical nature of the structure, but the structures arise in situations of great physical interest. Okay, and so in this class, I'm going to start by giving you perhaps the simplest example of a supersymmetric theory, the theory of supersymmetric quantum mechanics. We will study this theory and find many nice things about it. Yes? This wouldn't work without the Z2 gradation. I don't know of a theorem saying that there isn't, but I've never seen anyone discuss it. Z2 I think is somehow special. Mathematicians may even have proved some no-goes, but I don't know. Okay, these things are what mathematicians call Lie superalgebras. And we will come back to the study of Lie superalgebras in a more serious way when we start studying the superconformal algebra at some point. Okay? Right now this is just a teaser, to set you with the mathematical structure. Okay, fine. So now we're going to let go of mathematics for a minute, for a while, and turn to studying a simple physical situation which has supersymmetry and has already a lot of interesting physics. The reference for this part of my talk is this paper by is this paper by Witten called Dynamical Breaking of Supersymmetry. (1981), Nuclear Physics B. You don't need the whole reference, right? It's Witten. And also a follow-up paper by him, which is called Constraints on Supersymmetry Breaking. Okay. Oh, I mean, yeah.
So not just commutator and anti-commutators have this Z2 symmetry, also the products, right? If I have a product of two.
If you have a product of two objects, yes. Though for my consideration of the Jacobi identity, I didn't need to say anything about products. All that ever appeared was this bracket. But it's true that when we study these operators acting on a Hilbert space, the product will have that structure, yes. It's in fact, the vector space itself, the Hilbert space itself will have a Z2 gradation. States in the Hilbert space will be broken up into fermions and bosons. And fermionic operators are those which are off diagonal in this space. So let me just say that. So when we actually study supersymmetric theories, we will look at states like this, where all states are either bosons or fermions. Okay? All operators are matrices that act on this space. Okay? The fermionic operators are operators that have only elements here. Okay? And bosonic operators are operators that have only elements here. And because of that, the product of any two fermionic operators will be bosonic, and vice versa, and so on. Okay? So the Hilbert space itself has this Z2 gradation in every situation of physical interest, and then that it lends this gradation to operators. Okay. Great. So now let's start with a simple example. Consider the theory of the quantum mechanics, non-relativistic quantum mechanics in one dimension, of a particle in one dimension, moving on a line. Okay? So we're looking at the quantum mechanics of a particle in one dimension moving on a line. The coordinate on this line is called x. Okay? The one slight kick in this problem is that it's not the quantum mechanics of a one component wave function, but the quantum mechanics of a two component wave function. For instance, an electron with spin. Non-relativistic electron with spin, two component wave functions. Right? So the wave functions of our problem are psi, which are of the form psi1 and psi2. Each of psi1 and psi2 are ordinary Schrodinger functions, they're functions of x. Okay? So our whole Hilbert space is square integrable wave functions here and square integrable wave functions here, or equivalently tensor product of a two-state system with an ordinary square integrable wave functions and a line. Okay. Now, on this Hilbert space, I define the following two operators. Q1, which is equal to half P sigma 1 plus sigma 2W, and Q2, which is equal to half P sigma 2 plus sigma 1W. W is a function of x. Okay. If I was more systematic, I would consistently write big for operators and small for quantities and so on. Operator quantity, all same notation. Let's make it small. It's an operator here, but you understand. Okay? At the moment, I've just defined these operators. Fine. Now, let me compute, these are going to be two supersymmetry operators, two odd operators in this odd-even split. Okay? What I'm going to do is now, because of that structural rule, I'm supposed to compute brackets of these operators in order to understand what's going on. Okay? So I'm going to start now by computing the bracket of, let's say, Q1 with Q2. The bracket is an anti-commutator.
Okay, at this point, are you defining anything? What is P, sigma, and W are?
Oh, I'm sorry, I should have said sigma is sigma 1. It's the Pauli matrix sigma 1. Okay, so sigma 1 is equal to 1, 1, 0, 0. I hope I got that right.
Yeah.
Yes. Okay, sigma 2 is the Pauli matrix sigma 2. And P is the momentum operator. P is minus IH cross del by del x. We're just doing ordinary one-dimensional quantum mechanics, non-relativistic quantum mechanics. So it's all very explicit. Okay, excellent. Let me compute Q1, the anti-commutator of Q1 with Q2. Okay, so that is the anti-commutator of this guy with this guy. Okay, now P's commute with P's, so that P square goes outside. Then the anti-commutator of sigma 1 with sigma 2 is 0. From the Pauli algebra, which tells us anti-commutator of sigma I with sigma j is 2 times delta ij. Anti-commutator. Yeah? Okay. So this is 0. What about this guy with this guy? Okay, wait, let's go do the easier one first. What about this guy with this guy? Since both these are function only of x, these commute with each other, so they effectively like numbers, they go out. And then anti-commutator of sigma 2 with sigma 1 is again 0. Is this clear? So what remains is this guy with this guy and this guy with this guy. Okay? So let's write that out. So that's P sigma 1 square, so that's just identity. Okay? P W of x. Okay? Plus so that's, I want Q1 so let me do this guy with this guy and this guy with this guy. So P sigma and this guy with this guy is plus W of x P. Okay. And then we've got a 1/4 here. So that what I've done so far is write Q1, Q2. Okay? But then I need to write also 1/4 Q2, Q1. So that gives me same. Yeah, this should have been 0. Just 1 minute. Just 1 minute. And why I've just a minute. Sorry, just a minute. Sigma 1 P with W. That's correct. Just a minute. Okay. P sigma. Sorry, what's going on? One of them is a minus. Thank you. Yeah. Now it's good, right? Because this guy gives us minus PW. This guy gives us WP. But when we do it the other way around, okay, we'll get minus WP. Okay, and then plus PW. These two cancel each other. They're minus of each other. Okay, so thank you. So I got the two operators. Now I have them right. Okay? Wonderful. So we found our first anti-commutation relationship. Yeah. We found our first anti-commutation relation. The relation is Q1 anti-commutes with Q2. Let's now find Q1 square, okay, which is the same as half of anti-commutator of Q1 with Q1. Okay? Well, what about Q1 square? Well, first thing we get this term here. So this guy with itself. So that is equal to 1 by 4 p square. Then we get this term with this term. So there's 1 by 4 is there, so plus w x, the whole thing square. And then we get this with this and that with that. Right? So we get plus pw sigma 1, sigma 2 plus wp sigma 2, sigma 1. All good? Okay. Now we flip this around. Okay, so that's minus of sigma 1, sigma 2 times this. Okay? So this would have been 0 had p and w commuted with each other. But they don't commute with each other. You imagine this is a derivative acting on w and the wave function, whereas this is a derivative acting only on the wave function. The derivative acting on the wave function cancels, but the derivative acting on w remains. Okay? So what remains is this. So what we've got is q1 squared is equal to 1 by 4. So let's write it as 2q1 squared, or q1 anti-commutator q1 is equal to half p squared plus wx, the whole thing squared, minus ih cross, minus ih cross. Okay, now, but I'll also write what sigma 1 times sigma 2 is. Sigma 1 times sigma 2 is I times sigma 3. So the minus I cancels, so plus w prime of x times sigma 3. Is this clear? Okay, and it's very easy to convince yourself that the same algebra works also for Q2. So 2q1 squared, so 2q2 squared is also equal to the same thing. It's the same algebra. Okay, so what we're going to do now is define this operator by a symbol. It's a bosonic operator. I'm going to call it H. Okay? I'm calling it H because we're very soon going to make it the Hamiltonian of our system. Okay? And what we found is that Qi, anti-commutator Qj, is equal to delta ij times H. Okay? Now, it is an easy job to complete the brackets of our system. I leave it as an exercise for you. Oh, maybe I should do it. Okay. First, I'm going to claim Q1 with H is equal to Q2 with H is equal to 0. Okay. Why is this true? It's trivial. Can somebody give me an immediate argument? Very good. Who was saying that? H is? Q1 square. Lovely. So here you use H as Q1 square. Q1 obviously commutes with Q1 square because the two terms are Q1 cube minus Q1 cube. Right? Any operator commutes with any function of itself. Right? For this thing you use that H is Q2 squared. Once again the same argument tells you. Okay? And of course H commutes with itself. So now our Lie superalgebra here has 3 operators. 2 odd, Q1 and Q2, and 1 even, H. And we found all the brackets between the corresponding operators. Every operator, H commutator H is 0. H commutator Q1, H commutator Q2 is equal to 0. H commutes with everything here. But Q1 and Q2 anticommute with each other. However, Q1 squared and Q2 squared equal H. What we're going to do is to use this algebraic observation. So far we've done no dynamics, right? This is just some mathematics of differential operators, differential and 2 cross 2 operators. But now what we're going to do is to say, well, suppose we have a system, a one-dimensional system on this Hilbert space, whose actual physical Hamiltonian is this H. So H is equal to Hamiltonian. Now, in this problem, we've got a new kind of symmetry algebra, this Lie superalgebra, which has these 2 odd elements and the Hamiltonian. And there's this interesting interplay between the energy operator, the Hamiltonian, and these odd operators, these supersymmetry operators. In particular, the Hamiltonian has become sort of like the square, or is the square of supersymmetry operator. So supersymmetry operators, in some sense, is like the square root of the Hamiltonian. Okay? What is this good for? In a system like this, can we use these facts to say anything about the system that we would not ordinarily have been able to so easily say in a generic quantum mechanical theory? It's the question we're asking. Okay? Great. So the first question we're going to ask ourselves is about the lowest energy, the energy spectrum of this theory. You know, if you come for the TIFR entrance interview, chances are somebody will give you a quantum mechanical problem and say, what can you tell me about the spectrum of this theory? So we could say, give this one and say, what can you say about the spectrum of this theory? Okay? Well, the first thing to note here is that Q1 and Q2 are Hermitian operators. Right? Obviously, because P is Hermitian, sigma 1 and sigma 2 are Hermitian. Okay? So Q1 is a Hermitian operator, and the Hamiltonian is a square of a Hermitian operator, and therefore is a positive definite operator. Okay? So all the eigenvalues of the Hamiltonian are positive definite. Right? Just because any Hermitian operator can be diagonalized, its eigenvalues are all real, but then you square it, those real eigenvalues all become positive. Okay? Clear? So already we've learned one thing immediately from this in this trivial example, that EM, the energies of all eigenstates of this problem, are greater than or equal to 0. Immediate. Okay? Next question we're going to ask, what can we say about the 0 energy eigenstates of this problem? Okay. Actually, yeah, fine. Let's do it in bits. What can we say about 0 energy eigenstates of this problem? We're going to following Witten, we're going to approach this problem in steps. Actually, one can say something exact, very fast and very simply about this problem. But you know, we're not so interested in this problem as using it as a starting point to understand what's going to happen in many other problems that we will study through this course and you will study through your life. So we're going to de-emphasize at the moment things that are very special to this problem. Okay? But I'm going to start and try to do it slowly. So the first thing that we're going to ask is, suppose I was looking at this problem classically. And I asked for the classical, you know, I plotted this potential. So this is standard kinetic term, it's a mass 1 particle, okay? Could easily restore the mass if you want. So what is this? Of course, it's a problem of quantum mechanics of a particle moving on a line under the influence of the potential W square, and then some funny stuff, that W prime thing, causing spin flips. Okay? You think of this, I don't know, like a magnetic field, or something like that, right? Not quite, some magnetic field in the x direction maybe, causing spin flips. It's quite a familiar kind of problem, right? Notice that the magnetic field, this funny guy, has an H cross here. So if we were going to try to understand this classically, we just put that term to 0 in our heads. Okay? And look at the problem classically. So we look at this problem classically, and what we see is just the motion of a particle in a potential Wx squared. Okay? So suppose suppose I've got a graph of a Wx which does this, then the potential will look like this. The fact that the potential is a square is the classical analog of the statement that the spectrum of the Hamiltonian is always positive. Okay, so you see that classically the lowest energy configurations are those where W is smallest in magnitude, and zero energy configurations happen if and only if W goes to 0 somewhere. So the points where W vanishes, the zeros of W, are the classical zero energy configurations of this problem. Clear? Classically, both spins at that point would be zero energy. Of course, classically there's no spin, but okay. So that's a bit of a stupid statement, but okay, fine. Now let's say we graduate from classical to semi-classical physics. Okay, we go to the neighborhood of one of these zeros and ask, including doing perturbation theory at h bar, to check if there really are zero energy states. Okay, so how do we do that? So suppose there is a point xi such that W of xi is equal to 0. Okay, so in the neighborhood of xi, W in the neighborhood of xi goes like x minus xi and some coefficient, I'll call it lambda I. Okay, because it vanishes generically, it will have a linear coefficient. Suppose this was the case. Okay, now let me take this problem and expand it in the neighborhood of the minimum. This should be good enough in perturbation theory to study the question of whether the minimum really has, whether there really is a zero energy state around the minimum. Okay, so I go and I expand it. So what do I get? I get the Hamiltonian half, which is p squared plus lambda I squared x minus xi, the whole thing squared by by nothing, and plus h bar W prime, so that's lambda I sigma 3. Right, I'm working Taylor expansion around the minimum. Note that, why is this the same as perturbation theory? You see, classically a particle can be just at a point. Quantum uncertainty makes it fuzz out. But how much it fuzzes out is controlled by h bar. If we're doing perturbation theory in h bar, you just look at the neighborhood of that point, go further and further away. Right? So, all good. Now let's work out the spectrum of this problem. That's terribly easy. Please.
So you are assuming that W has a non-zero first.
I'm assuming W has a non-zero first derivative. We will later do an analysis which makes no assumptions. But for now, I'm assuming that in the neighborhood of the zeros, there's a non-zero first derivative. Yes. And for every zero. Okay. So now let's look, what is the spectrum of this? Well, this is really a TIFR entrance interview kind of question. This is a harmonic oscillator. Okay, so its spectrum is h bar lambda I into n plus half. Okay, and then we get the spectrum of this, which is plus h bar lambda I into plus minus half. Plus minus, half. Have I missed a half somewhere? Have I missed a half? Plus minus 1. But it's not giving me the answer I want, so I just went. Plus minus, let me check. No, there was a half there. Yeah, because of this half, this half. Okay? Plus minus half. Now, you see, once I start taking a harmonic oscillator and going to higher energy states, just doing the Taylor expansion around the point is ridiculous, or could be ridiculous. Okay? But for the ground state, it's perhaps a reasonable approximation, because that's the particle just being there and then fuzzed out by quantum. So let's forget the n business. I'm looking at the lowest energy state. Ground state. It's this. Now you notice something very interesting. You notice that, okay, now I should be a little more careful here, because this was lambda I, and then I should have put a mod lambda I. Because that energy doesn't matter, doesn't care about the sign of lambda I. But this one did. This was genuinely lambda I. Okay? So you notice that no matter what lambda I is, and in particular no matter what its sign is, there is always one spin, one choice of spin, for which this ground state energy vanishes. Okay? So let's write that down. If lambda I is greater than 0, okay, so I'm going to draw a diagram. If W was cutting the x-axis like this, so lambda I is greater than 0, then in that case this is positive, so we have to choose the minus. So it's this state, 0 energy for this guy. The doublet that had eigenvalue of sigma 3 equals -1. Okay. On the other hand, if lambda I is less than 0, okay, this remains positive, but this is negative. So E is equal to 0 for 1, 0. Okay? Excellent. And this we will draw with the diagram like this. Right? So every time W goes and cuts like this, you get a 0 energy state, but its doublet is 1, 0. Every time W goes and cuts like this, you get a 0 energy state, but its doublet is 0, 1. All good. Okay? So within semi-classical perturbation theory, okay, first order in the semi-classical perturbation theory, we get as many 0 energy states as the number of zeros of the function W, and they have sort of alternating spins. Why alternating? Because in any graph for W, suppose this is a graph for W, a 0 like this will be followed by a 0 like this, and then a 0 like this. So the spins of the 0 energy eigenstates alternate. Okay? So we seem to have discovered a beautiful rule in perturbation theory. Okay? That every 0 of W leads to an exact ground state of the system. Why do I say ground state? I say ground state because we know that there's no state with energy less than 0. So if you find a 0 energy eigenstate, it's ground state. So every 0 of W leads to an exact 0 energy ground state of the system, and they come with these alternating spins. Okay, this sounds wonderful. Now, so if you were, you might think, okay, that's cool, we've got real control over the 0 energy eigenstates of our problem. And you might think, if you were doing the analog of what we do in field theory, you might think, well, this is nice. You might think, well, this is nice, but how do I know that if I go to the next order in H bar, one of these 0 energy eigenstates don't pick up a little energy? Okay? And in fact, one could do the calculation. One could do a 2-loop. This is like the analog of a 1-loop calculation. Okay? By the way, the fact that this
Sorry, what was the previous statement about the ground state? That every 0 has an alternating.
Firstly, every 0 of W, there are as many ground states in perturbation theory as there are zeros of W, and that they come with alternating spin. The wave function for them comes with alternating spin. Okay? By the way, the fact that, you see, something sort of interesting is happening here. It looked like we were going to get non-zero energy because of the harmonic oscillator energy of the boson. But that was cancelled by something. And there's something, as we will see in more detail as we go on, we will be able to think of as the harmonic oscillator energy of a fermion. And the fact that you get 0 is this famous thing that happens in supersymmetry. namely the fermionic and bosonic harmonic oscillator energies cancel each other. In what sense is the fermionic harmonic oscillator? We'll come to. I will explain to you. Okay? Good. So, now, if you were, you might think that this is sort of cool, but you might want to test this to higher orders in H-bar. I will give you an argument within 10 or 15 minutes that will convince you that even without doing the calculation, that no matter what order you go to in H-bar, you will always see this, that at each of these points there's a zero energy eigenstate. However, order by order in H-bar is not all of life. There might be non-perturbative effects. Is this statement that we've found from semi-classical analysis correct? Is it correct that the total number of ground states is the number of zeros of W? Or, is this sort of non-perturbatively destroyed? Now, this is such a simple model that we can easily answer that question. So let's answer the question now, doing what, some of you may have been thinking from the beginning that this is what I would have done to answer the question about ground states. And that's this. Okay, so the thing that you might, that we can sort of do immediately is the following. I'm looking for zero energy eigenstates of my system, so I'm looking for solutions of the wave equation H psi is equal to 0. But H I know is equal to Q1 square, also Q2 square, but it's the same thing. I mean, it's the same thing and you don't get any new information by writing it as Q2 square. So we'll write this as Q1 square on psi is equal to 0. But you see, suppose Q1 squared on psi is equal to 0, then I put another psi on this side. Using the fact that Q1 is Hermitian, this is the same as mod square of Q1 on psi. Okay? The only way that the norm of a state can be 0 is if the state is 0. So the only way that H can be 0 is if Q1 on psi is equal to 0. Okay? So the problem of finding zero energy eigenstates is the same as the problem of solving the differential equation Q1 on psi is equal to 0. Okay? Now, this is a very simple differential equation to solve, unlike H psi is equal to 0. Or H psi is equal to E psi. Why is it so simple? It's simple because Q is a first order differential operator, whereas H was a second order differential operator. Now, first order linear differential operators equations can always be solved by integration. Sometimes by putting an appropriate integrating factor. We won't even need to do that, as you know. So this question, Q psi is equal to 0, we can just solve, right? It's a differential equation. We can solve it. So let's solve it. Note that this trick does not help us to find the spectrum of the theory. It only helps us to characterize the ground states, the states annihilated by the supersymmetric operators. These are what we will call supersymmetric states of the theory. So there's something what's special about supersymmetric states. They're much easier to deal with than the non-supersymmetric states. Right? For the non-supersymmetric states, we still have to solve Q1 squared on psi is equal to E psi. And the fact that H is Q1 squared is nice. It tells you that the eigenvectors values have to be positive, but doesn't help you to solve. But for the ground state, it converted a second order differential equation to a first order differential equation to help us to solve. Okay? For the supersymmetric states. Okay. And so now what was Q1? Well, that was half, but half doesn't matter. So let's forget half. Then there was sigma 1p plus sigma 2w on psi is equal to 0. Okay. So now I multiply this whole thing through by sigma 1 from the left. So sigma 1, sigma 2 is I times sigma 3. So I get minus I h del by del x. It's just d by dx. It's only one x in the problem here. But okay, minus I h d by dx minus I plus I sigma 3 W on psi is equal to 0. Okay. Now, had there not been a matrix here, we would have just solved this by integrating, right? But actually, the fact that there's a matrix makes no difference, because the matrix is not a function of x. It's just one matrix. Because one matrix commutes with itself. It's like a number. So we can just integrate. Okay, so the solution to this equation is psi is, so first I'll cancel the, it's basically the same as the equation h bar d by dx. Psi is equal to I sigma 3w, sigma 3w psi. Have I got the sign right? I think so. And therefore, psi is equal to exponential of integral, sigma 3 outside, integral w of x from some starting point, let's call it 0, but it could be anything, to x, acting on some psi naught. What have we concluded from this? First, so we've solved the differential equation. We've got an answer. H bar by h bar here. Yes. Thank you. Okay. So we've solved the differential equation. We've got an answer, and you might think, well, this is strange, because when I was doing it semi-classically, I got many ground states depending on the number of zeros of W. Here I'm getting sort of a unique ground state, not quite a unique, 2 ground states, because I could have chosen psi 0 to be 1, 0, or I could have chosen psi 0 to be 0, 1. So it looks like I'm getting 2 ground states always. What's going on? First, are we getting 2 ground states always? This is a formal solution. But it's very important in quantum mechanics that not every wave function you write down is a wave function. Wave functions have to be normalizable. If you forgot about that, you could do wonderful things in quantum mechanics. For instance, you could take a harmonic oscillator and solve the equation A dagger on psi is equal to 0. That's a first order differential equation, gives you an answer that blows up exponentially, like e to the power x squared at infinity. But if you allowed that, you would use the fact that the Hamiltonian is A dagger plus A dagger A to conclude that that state had energy minus h bar omega. That's an interesting story about what our loop quantum gravity friends once did by making use of this incorrect theorem. But I won't tell you that on camera. Okay, so I mean, you can get ridiculous results in quantum mechanics. You know, a thing about the harmonic oscillator is that its energy spectrum always has positive energies. If you forget about this normalizability condition, you can get anything you want. So normalizability is not just something to make the mathematicians happy. It's really important. Okay? Now, let's check whether our wave function here is normalizable or not. Okay, let us suppose that this W goes large in modulus at plus minus infinity. So that we're looking at a theory which will have, no continuum in the spectrum. Right? W going large in modulus told us that the potential, which was W square, remember, is going to infinity at plus minus infinity. Let's suppose that that's the case. The question is W going to large positive infinity or large negative infinity? And that makes a great deal of a difference. You see, suppose for instance, W was a function like this, that went to large positive infinity, both for large positive x as well as large negative x. Suppose that was the case. Then you see that this quantity here will be positive at positive x, but positive and large at positive x, but negative and large at negative x, because the integral is going from 0 to minus x, to a negative number. Or another way of saying it is that, for instance, if this was an even function, this integral would be an odd function, would have opposite signs. Clear? Okay. Now, you might worry that, already the fact that it's going to something large and positive at positive x bothers me. It looks like it's not normalizable. But you have to be careful, because apart from this, there's also sigma 3. Now, sigma 3 could take the value either plus 1 or minus 1, depending on whether psi 0 is 1, 0 or 0, 1. So the fact that it goes to large positive at a positive infinity, it's not a problem. Because then you could choose then the psi 0 to be equal to 0, 1. And then this thing would be nice and normalizable at positive infinity. But the same choice, psi 0 was constant, so we get to choose it once. The same choice will lead to trouble on the other side, because it was becoming negative there. Sigma 3 switches that to positive and makes it non-normalizable on the other side. Is this clear? Therefore, a potential like this, where W goes to positive infinity on both sides, never leads to a normalizable wave function. It's the same the other way. If you flip this around, W going to negative infinity on both sides, once again there will be no choice of psi 0. That will give you a normalizable wave function. You just switch which one was positive, which one was negative. However, if W did this, it was large and negative here and large and positive here, then the integral here is negative at positive x, and so we choose 1, 0. The integral here is also negative at negative x, because this function is positive, but we're doing the integral backwards. So it's negative at negative x also. So this same choice makes it nice and normalizable on both sides. Okay? Flip it, and we would have to choose, instead of 1, 0, we'd have to choose 0, 1, but we'd reach the same conclusion. Is this clear? So what we have concluded is very unlike our semi-classical analysis. The exact answer tells us that the question of whether the answer to the number of supersymmetric ground states in the system is either 0 or 1. It's 0 if W either increases or decreases on both sides. And it's 1 if it does, the other thing. Is this clear? There's another way to say it. And that other way to say it is this. Notice that doing the other thing is same as having an odd number of cuts in the real axis. Whereas going the same way is same as having an even number of cuts, might be 0 cuts on the real axis. Okay? So if the number of solutions to the equation W of x is equal to 0, so if we try to solve the equation, W of x is equal to 0. Okay, we try to solve this equation, and we find number of solutions is equal to even. Answer is that there are no supersymmetric solutions, no ground states, no SUSY ground states. Number of solutions, we find one SUSY ground state. This is quite sort of dramatic, right? We had this semi-classical analysis, which seemed so nice, told us every time there was this, every time there were these classical cuttings of Wx with the x-axis, every time there's a solution Wx equals 0, we got a nice semi-classical ground state with these odd and even flips and spins flipping and so on. And we find that, okay, if these come in even numbers, somehow they're just all lifted. exactly, because we've done exact analysis. It's nothing imprecise about what we've done. It's just completely exact. Now you might wonder, could this lifting actually have happened in perturbation theory? Okay? Could this lifting have happened in perturbation theory? The answer is no. You see, perturbation theory, suppose I have a local cut like this. If this just continued downwards forever, this would be an actual ground state. However, if it did the same thing and then later decided to come back up, it would not be a ground state. Perturbation theory explores greater and greater sizes in the neighborhood of this point. But I can choose these two potentials to be exactly the same, you know, in some region and then turn it around. So perturbation theory cannot see the difference between this and this. So in perturbation theory, you will never see the lifting of the ground state.
It is always an option. For
Perturbation theory will always find a zero energy ground state.
because it's an odd solution.
Because perturbation theory doesn't know whether later on it's going to become an even solution. But it's always a Taylor expansion. Okay, well let me take my potential and make it non-analytic. And just in a neighborhood, these two are identical, and then I, you know, make fifth derivative discontinuous and take it upwards. Perturbation theory, the Taylor expansion cannot see that. Okay? So this is actually a genuinely non-perturbative effect. And one can actually understand that more clearly. It comes from instantons or tunneling. It's a tunneling effect. It's e to the power minus 1 over h bar effect. And maybe if I get down to writing problem sets for the course, which I will, I'll set a problem on this. I'm trying to see how tunneling effects, how these instanton effects lift these ground states. Okay?
In perturbation theory also you can do this, but
Use in non-perturbative perturbation there, using instantons. Yeah, it's an instanton effect. Okay? Of course, the fact that these states were there in perturbation theory tells us that there must be low energy states non-perturbatively. Right? So the question you could ask is, okay, maybe they lifted, but what is their energy? H to what power? And the answer will be e to the power minus 1 by h bar. It's like a double well problem, right? The degen, you know, it's that same thing. But it happens in a very nice way. And does not happen completely randomly, because if there is odd number of cuts, one guy stays. It's a linear combination. Okay, good. It's a good question. That's a good question. You see, what you can do is analyze it in the neighborhood of each of these points. We've got the exact wave function. Right, this is the wave function. Now you can analyze it in the neighborhood of each of these points. And in the neighborhood of each of these points, it's a good question. It's a good question. The question is it mostly one of the solutions? You see, one of the things we can see immediately here, which is, you remember that the various solutions had different spins. This solution has a definite spin. Okay? So I think it will turn out to be a linear combination of the guys with the same spin. Do you understand what I mean? Let me say it more clearly. Yeah, some sort of linear combination of those guys, but not the alternate guys. Okay, so what I mean is that suppose we had this guy. Suppose we had the situation where there was one state, and according to our rule, we had a nice rule here, right? Let's see if it's still around. Actually, this is the reason I'd written that rule, but then it disappears. sorry, here. This guy was a 0, 1, according to our rule in perturbation theory. This guy was a 1, 0, and this guy was a 0, 1. Now let's look at this. In this case, this was negative at infinity, so this is negative. So we need a 0, 1. No, we need a 1, 0, 1, 0. We need a 1, 0 because it has to become negative at infinity. It was already negative, so we need a 1, 0. Okay, so in this case, it will be mainly this guy. Because the other, in the neighborhood of the other two guys, there was no nearly zero energy state with that spin. And the spin is the same all through. If there were many kind of cards, I think it will be a linear combination of all those with the right spin. But I would have to confirm that. Okay. Excellent, 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 excellent. Now, this is great, but you might think, okay, so we did a calculation, we got a wrong answer. In this particular case, since things were so simple, we did the right calculation, we got the right answer. But you know, wasn't there any information in our wrong calculation? You know, in real situations, when I'm studying supersymmetric QCD, I won't be able to do the analog of solving for this wave function. But I will be able to sometimes do the analog of the first thing, solving semi-classically. So could I use the information in the semi-classical analysis to get, if not at the full right answer, you know, something about the right answer? Okay? And you can. And that's what we're going to talk about now. We're going to talk about what is called the Witten index. Okay, so let's go. Yeah, go on, ask. So these states sitting around W equals 0 were all degenerate because they were all zero energy states. And indeed, it is the mixing in this degenerate manifold that leads to lifting of eigenstates. However, not randomly. They don't all go away. You know, there's more than that. It's true that this is, if you work out the instanton calculation of the tunneling, that's what you will find, right? You will take this. You see, since these states are all semi-classically degenerate, you can forget about all the other states in trying to find, to good approximation, you can diagonalize the problem in this subset. Because mixing with the other states will be highly suppressed compared to mixing between these states because of the energy denominators. Okay? So now it's a problem just restricted to this. And you want to know what the matrix elements are. And these instantons will give you these matrix elements. So indeed, it's what you're saying. But notice that if we just said it that way, without any of the structure of supersymmetry, you tend to think, well, generically, they'll all be lifted. There's more structure than that, right?
But even by doing perturbation theory, we should have taken care of the fact that we are using degenerate.
Well, maybe we're using perturbation theory in different language. But when I say perturbation theory here, I mean a power series expansion in H bar. In a power series expansion in H bar, you will never see it. Now, you know, since we're talking about quantum mechanics, maybe by perturbation theory here, you're thinking of perturbation theory the way Schiff thinks of perturbation theory. Not keeping track of how big or small the matrix elements are, but just doing perturbation theory in this. In that way, you will. But that's not what I mean by perturbation theory. What I mean is semi-classically, in the H bar expansion, power series expansion in H bar. The kind of perturbation theory we would do with Feynman diagrams, you know, loop expansion. Is this clear? Okay? You will see these guys get non-zero energies, but at order e to the power minus 1 by H bar. So that's something you will not access at any order in a power series expansion in H bar. That's what I mean by non-perturbative. Okay? Good question. Other question? Yes? What?
classical states which you found
W-
are not
In one case, not normalizable, so it's not a state. In the other case, there's one state that is normalizable. So,
half the semi-classical states which we thought are good as not even normalizable if you do an exact analysis.
half the semi-classical states, more than half in some sense. But you see, what's going to happen, Sunil? It's not that these states will just go away. They will just get slightly non-zero energy. You see, in our exact analysis, what we are doing is solving the problem of something having exactly zero energy. So, nothing ever just zooms off. What? There will continue to be a manifold of low energy states. I mean, not manifold. There will be as many low energy states as there were zeros of W. It's just that the question of whether a state is exactly zero energy or not, that is a very sensitive question, right? If you think about it, that's the kind of question that we almost never routinely address unless it's a very simple model. We're talking about something being exactly something. In this problem, we can solve it. Is this clear? Yeah. Okay, excellent. Okay, so now that I understand the structure of this problem reasonably, I want to go back to the algebra of the algebra I had, my supersymmetry algebra. So I want to go back to the supersymmetry algebra and study that a little more. So I had this algebra which was Qi, Qj was equal to H, and then H commutes with everything. Okay, now I'm going to ask the following. Suppose I have a state at, what's unusual about this is the following. The symmetry algebra in our problem involves the Hamiltonian. That, if you think about it, is something you've not seen before unless you've seen supersymmetry. Maybe you have in some way if you think of conformal invariance. Okay, but it's not very usual. It's not a very usual thing. It's not when you do SU2. The symmetry algebra was SU2. Okay? So states, Hamiltonian had nothing to do with that. It's not like an SU2 generator squared to an, you do something to the SU2 and you get the Hamiltonian. Okay? So what I want to do is to try to see what I can say about the representations in which states appear, given the fact that we know this algebra must be implemented in the Hilbert space. Okay? So states of two sorts, as we've seen, there are states with E is equal to 0, and there are states with E not equal to 0. Okay, how is this algebra implemented on states with E equals 0? Firstly, because all operators commute with the Hamiltonian. The statement that we're looking at the implementation of the algebra on states of a definite energy is a consistent thing to do. Because if the operators didn't commute with the Hamiltonian, then acting with an operator on a state of one energy would take you to a state of another energy. But since everything commutes with the Hamiltonian, okay, this is a consistent thing to do. We can look at the representations energy by energy. Okay, so let's first look at E equals 0. What is the implementation of all these operators on the subspace of states with E equals 0? Well, H is implemented by 0 because H is its eigenvalue, which is 0. Okay? And what is Q1 implemented by? 0. It's a good, fair guess when somebody in a course asks you, what is the answer to this question? 0, infinity, 1. Usually it's one of those, right? Okay? So clearly it's 0 because we argued, right, that Q annihilates states that Q1 annihilates states that are annihilated by the Hamiltonian. So Q is also Q1 is also implemented by 0. So is Q2. So it's a very trivial implementation of this algebra. All three operators are just 0 on that subspace. Okay? So that is the implementation of this algebra on zero energy states. What about on states of some non-zero energy? Let's call this non-zero energy epsilon. Okay, so when on this subspace, let me, so I have q1 squared is equal to epsilon q, maybe epsilon by 2. Oh, it's a pain. Okay, let me write it in terms of anti-commutators. qi qj is equal to epsilon. That's what I have on the state. Just put it in the Hamiltonian as its eigenvalue on the state. Delta ij, thank you. Now, because this epsilon is a pain, let's define little qi, which is equal to qi divided by square root of epsilon. Square root of epsilon makes sense because epsilon is positive. Okay. So we define qi, which is this object. And now our qi, qj is equal to delta ij. Okay. ij run from 1 to 2. Okay. This algebra has to be implemented on states of any energy. Okay. Now, I want to know what are the irreducible representations of this algebra. Any guesses, by the way? Clifford. Good. Oh yeah, it's Clifford. Fantastic. So you guys already know the answer. You know that the irreducible representation is just two-dimensional. So maybe I can just appeal to that. I was going to show you. But yeah, that's a very nice comment. It's Clifford algebra, right? So, but yeah, okay, let me just say it anyway, since you might. You know, suppose I've got a state psi. I want to see in this energy subspace. And I want to see what other states there may be that I can get to starting from the state psi and acting with one of the symmetry operators. So, you might think, well, I can take psi, then I can take q1 psi, then I can take q2 psi, and I can take q1, q2 psi. I can't do more because if I take any q1 square, that's the same as 1. Because on the subspace q1 squared is 1. So the maximum possible orbit is a set of 4 states. I take some state I could maximally generate by these symmetries 4 states. But is it really 4 or is it less? Okay, so let's check. Let's look at this state and act on it with q1. So let's call the state chi. So q1 on chi is equal to q2 psi, right? Because q1 squared is just 1 on the subspace. It goes through. Yeah. Or commute the q2 twice through it. Each time gives you a minus sign, makes up, and then q1 squared on psi is 1. Okay? So q1 on chi was q2 psi. Okay. But q1 on psi was chi was q2 psi. Wait, now I wanted to argue that there was another object which acting on q2 psi. What is the adjustment? Just a minute. I made an argument. Now I can't remember it. Just 1 minute. I'm trying to argue that 2 of these that it's actually a 2-dimensional space. That these guys are. Sorry, just a minute. Let me see if I've written down my argument. Sorry. Okay, sorry. Let me not waste the time. Sorry, let's see. It's easy to convince yourself. I made a nice argument, I can't recall it now. But it's easy to convince yourself that this is a two-dimensional space. I'll give it to you next time. Okay? Instead of four. That these states are not linearly independent of each other. Blanking out at the moment, sorry about that. Okay. And the answer is just, as you said, Clifford algebra. Okay, so the space here is some two-dimensional space. Okay, and this two-dimensional space is the space in which, for instance, this guy is generated by, this guy is implemented by sigma x, and this guy is implemented by sigma y. Right, sigma x, sigma y obeys this algebra. This is a two-dimensional space, and every representation of this algebra is sum of copies of this two-dimensional space. It's the same thing as somebody said, Clifford algebra. It's a famous result for Clifford algebra. I'm just trying to make that argument. I'm blanking out. I'm sorry about that. I'll give it to you next time. Okay, so that this algebra here in the space of E not equal to 0 states is a bunch of copies of Clifford algebra of this two-dimensional space. So this Q1 is sigma x and Q2 is sigma y on this two-dimensional space. Okay, so the whole Hilbert space of our theory is decomposed as follows. There are these singletons at E equals 0, where all operators are implemented by 0. And then there are at any energy, there's a bunch of these two-dimensional subspaces in which we've got Q1 and Q2 acting in this way. Okay. Now, suppose we could find an operator. Suppose we can find an operator which I'm going to call minus 1 to the power f that anti-commutes with every supercharge, with both Q1 and Q2. Suppose we could find such an operator, and I'll find it for you in just a minute. Okay, so suppose we could find an operator such that this operator anti-commutes with both Q1 and Q2. Okay, and also commutes with the Hamiltonian. It's guaranteed that it also commutes with the Hamiltonian, because if it anti-commutes with Q1 and Q2, then it commutes with Q1 square, but Q1 square was the Hamiltonian. See, I don't have to say that, also commutes with the Hamiltonian. Okay? If I can find such an operator, then if I consider the object trace minus 1 to the power f times e to the power minus beta h, this trace here receives 0 contribution from each doublet. Why is that? Because the two states in a doublet are taken to each other by the action of one of the q's. And since minus 1 to the power f anti-commutes with each q, if one of the states in the doublet of this representation doublet, if one of the states in the doublet carries minus 1 to the power f 1, the other state will carry minus 1 to the power f equals minus 1. Okay? Since both states in the doublet have the same energy, this factor here is the same for both states in the doublet, but this guy is 1 for one of them and minus 1 for the other one. And so doublet by doublet, it just adds up to 0. Sorry, was there a question? Okay. Okay? Is this clear? So, what we just take this object, evaluate it on the Hilbert space of our theory, because it breaks up into these singlet and doublet representations. Every doublet gives us 0. just manifestly. All that remains are the singlets. All that remains are the singlets. Singlets, remember, were the zero energy states. So this quantity here receives contributions only from the zero energy states and equals the number of zero energy states for which minus 1 to the power f is 1 minus the number of zero energy states for which minus 1 to the power f is minus 1. Okay? Now let's go back to our problem and see if we can find such an operator. I said suppose there was an operator. Can we find such an operator? It's very easy. Let us see. Let us remind ourselves that Q1 was equal to half sigma 1p plus sigma 2w, and Q2 was equal to half sigma 2p minus sigma 1w. Any guesses for what this operator could be? Well, how about sigma 3? Sigma 3 anticommutes with both sigma 1 and sigma 2. So it anticommutes with both of the supersymmetries. Okay? So this sigma 3 is what we're going to identify in our problem as minus 1 to the f. If you think of f as fermion number, what that tells you is that we're identifying this state as a boson and this state as a fermion. In what sense that is natural from a point of view that is more closely analogous to what we will do in higher dimensions, I will explain to you perhaps this class or definitely next class. It will come from writing not a Hamiltonian for this theory but a Lagrangian for this theory. When we write down a Lagrangian for the theory, we will have both commuting and anti-commuting fields. The anti-commuting fields will be the fermions of our problem. And the quantization of that fermion will give you this two-state system of 0 and 1. And so a fermionic state, and occupying the fermion will be 0, 1, unoccupying it is 1, 0. Okay, so this will be very natural from the language that we will routinely use when we study quantum field theory. But at the moment, it's just something. It's an operator that obeys all our conditions. Okay? So, suppose that, so the quantity that we were aiming to compute in general was this trace minus 1 to the power f e to the power minus beta h. In our problem, this is trace of sigma 3 times e to the power minus beta h. Okay, this quantity counts number of bosonic ground states minus number of fermionic ground states. Now, before we do any theory with this quantity, let's first do an experiment. Let us remind ourselves that if we computed this quantity semi-classically, we would get boson, fermion, boson for this. Oh, sorry, fermion, boson, fermion for this. Is this clear? And so, what we would get is, in a problem like this, so I'm going to write down an answer and you tell me if you believe it. In this problem, we would get trace minus 1 to the this Witten index. I'm going to call this I Witten index. IW is equal to minus 1. In this problem, okay, we'll get IW is equal to 0 because there will be as many fermion, boson, fermion, boson, fermion, boson, all cancel. Number of fermions minus number of bosons cancel. Number of bosons minus number of fermions cancel. In this problem, where we invert this, we will get IW is equal to 1. Right? Because this would be boson, fermion, boson, fermion, boson. And in this problem, okay, the fourth possibility, again we would get IW is equal to 0. This we got semi-classically. Now let's compare it to the exact answer.
Excuse me, sir.
Uh-huh.
There is a 4 o'clock seminar is there.
Seminar.
So 3:45 please.
3:45 we leave. Okay, thank you. Okay, yeah. Now let's compare it to the exact answer. Suppose we were in these two cases where we got 0, the exact answer also gave us 0 because there were no ground states. You remember, if the potential went like this or like this, there were no ground states. So 0 is right. Semi-classically, we got these two things right. What about these guys? Well, in this problem, I hope I'm getting the sign right, but we got exponential of integral W of x sigma 3. Okay, this went positive, so we needed a negative. So I'm sorry, I've messed up somewhere. We needed a negative, right? Yeah. This problem, I'm sorry, I've messed up. Hey, in the exact problem here, I'm getting this equals -1. I've messed up somewhere in there. Please do this carefully. You should get the same answer. +1 and -1 are opposite? Thank you. I will take your word for it. Okay. Sorry. This one was opposite, you're saying, right? Okay, great. So then this agrees. We get a -1 here, and the other way around also will match. So you see, while we have not managed to accurately compute the number of ground states semi-classically, we have managed to accurately compute this quantity even by doing crude semi-classical approximation. Why? Why was this quantity easier to compute? Why was this quantity easier to compute than the actual answer for number of ground states? Well, so we've got 7 minutes left. Let's try to finish in those 7 minutes. The answer to that question is easy to understand. Look, what was the spectrum of our theory? I'm drawing the spectrum in this funny way. This axis is energy, and every time I have a state, I will put a dot. So, and let's say I put a cross for bosons and a circle for fermions. Okay, so suppose that our spectrum of our theory was 3 crosses and one at 0 energy, and then there were a bunch of cross blob, cross blob, cross blob, cross blob. Suppose this was the actual spectrum of our theory.
Could you please what this cross and blob
They refer to boson and fermion.
Okay.
Remember, in a doublets, it's 1 boson and 1 fermion. By boson and fermion, I just mean -1 to the power f is 1 or is -1. That's what I'm calling boson and fermion. Okay? So, now suppose I took this theory and I changed a coupling constant in this theory. I did some continuous variation in my system under which the continuous variation is chosen so that the spectrum remains continuous. Nothing too drastic. Not like suddenly taking the potential which was up and then making it down or flat or something. Something not too drastic. We'll discuss a little bit what that means later on. Okay? But a change in the problem of the parameters of the problem so that the spectrum remains continuous. What can happen to this diagram? As far as the zero energy spectrum is concerned, there are two things that can happen. A cross and a blob could pair up and leave. Okay, so this could go off to non-zero energy. Or a cross and a blob could come from here and come down. So the number of zero energy states is not protected under continuous variations, because crosses and blobs can pair up and leave and come down. But the number of crosses minus the number of blobs at zero energy is protected, because all non-zero energy states appear paired with cross and blob. And the only way that energy states can appear or disappear continuously is for a cross and a blob to go or come down. So you see that while the spectrum, the zero energy spectrum of the theory is not a protected thing, it's not something that will not change when you make changes in your parameters of your problem. The thing that is the number of bosons minus the number of fermions at zero energy, that is very tightly protected. Okay? So if you can, in some limit, let's say you've got a nearly free theory, h bar goes to 0. Okay? You can compute the number of fermions minus the number of bosons in at zero energy. That will be reliable. Okay? Even though the actual numbers may not be reliable. So this is a much more robust quantity, this quantity. It's a quantity that you can compute in some other region of parameter space and then continue down to the region of parameter space you're interested in, and unless your variation of parameters is so drastic, like it's changing the asymptotics of the potential or something like that, if you're doing some reasonable variations, you're guaranteed that this Witten index will not change. And we see experimentally in this situation that our crude approximation, our crude semi-classical approximation, was able to correctly compute the Witten index, even though it was very far from being able to correctly compute the number of ground states. Okay? So maybe this is a, maybe it's, yes?
So when we change the so this fact that we got these higher energy states in pairs dependent on the algebra.
Dependent on the algebra.
So if we change the parameters, is it still?
No, you change the parameters in a way that preserves the algebra.
Yeah, but here, as you said, by taking h bar going to 0, we cannot do that, right?
Why not?
Then we wouldn't have anti-commutation in between.
Well, at any non-zero value of h bar, no matter how small, it's there. Okay, now you may be asking, could you make a clean argument that you had to get the right answer in the semi-classical limit? I think you could. I think you could. You see, because
Is the question that can we put an extra coupling constant in that third term?
which third term?
The interaction term?
No, we can't do anything else. Is that the question?
I mean, whatever h bar appears there will appear in the combination that is known. So then you are changing it simultaneously.
If that was the question, I agree with Shuman's answer.
Then everything is.
Okay, I thought it was a different question. Let's move on. Yeah, okay. Any other questions or comments? Yeah. The general argument is this, that things cannot change under continuous change of parameters. Okay? So, if you could do a continuous change of parameter, you could do something that would make this thing exact, make your semi-classical calculation exact. Okay? Then you know that you've done it correctly. Now, one way you could do that is the following. The general rule is, what kind of deformations of the potential are you not allowed to do? The general rule is you're not allowed to change behavior at infinity in a significant way. Okay? But you know, the way that you could make this exact, for instance, is by erecting infinite potential barriers between the two things that go off to arbitrarily large values. The way that this thing is suppressed, that the way the semi-classical calculation is corrected is through tunneling. And you could move to a region where the tunneling effect goes to 0. Okay? And thereby, in that limit, you would have a bunch of ground states that were exactly all 0 energy. Now, these won't all stay 0 energy as you allow for the tunneling. You move the barrier away. Some of them will leave, but they can only leave in pairs. That's basically the argument. Okay? So, to suppress the matrix element that would cause this, and you can reliably do that in the space of these potentials. Because in this quantum mechanics case, we could do basically anything to W of x. It was completely in our hands. Okay? As you will see in more realistic field theory, more interesting field theory situations, we sometimes have to do more other things, but we will see that as we go. Okay, good. I think we need to stop. Any other questions or comments before we? Okay, so next time I will give you a clear argument that the only algebra representation of the irreducible representations of that algebra are two-dimensional, and then we will move on. Then in the next class we will continue to study quantum mechanics. We will turn though to studying sigma models on manifolds, and we will find that the supersymmetry algebra is implemented by differential operators on these manifolds, and we will find a connection with de Rham cohomology and scalar geometry and all kinds of other fun stuff.